Hello and welcome to our lesson on logarithmic functions and graphs. This is going to be from section 9.4 in our text. We've got a lot of concepts to cover, so let's dive right in. We're going to hit each one of these formulas briefly, maybe give a short example, and then we're going to hit the examples from the textbook to give this a more in-depth coverage. So the first thing we have f of x equals log base b of x. That is how you read this formula correctly. Remember, f of x means y. So this is our standard basic logarithmic function formula. F of x, again, which is y, equals log base b of x. Standard form of a logarithmic function. Next, we have our what I call the converter formula, where we can take an exponential function and convert it into logarithmic form, or vice versa. This goes both ways. This is a nice handy formula to have on hand if you're converting from exponential to log or from log to exponential, either way. Next, two things that have to do with the calculator, either scientific or graphing. If you have an log button on your calculator, you need to know that that means log base 10. So log with no base showing is understood to be log base 10. Ln, that's the natural log button. Ln stands for natural log. It means log base e. So anytime you have log base e, you can simplify that to ln, which is natural log. Next two formulas are for simplifying logarithmic expressions. The first one says log of any base of 1 is 0. So if you're taking the log of 1, or the natural log of 1, or log of any base of 1, that's going to be 0. And log base b of b to the x equals x. This one is really super helpful, and I'm going to give just a brief example of that real quick. Let's say we have log base 3 of 3. So as you can see here, this log has a base of 3. The 3 that we're taking the log of has an exponent of 1, so that makes this 3 a base. And the way that I normally teach this, I say if the bases match, they cancel, and the exponent is your answer. So this basically says if you're taking the log and the bases match, the exponent is the answer. And the last formula is the change of base formula. So if you're taking the log of a number or a letter and you have what I call an unfriendly base, which means a base of something other than 10 or e, you can convert that logarithmic expression into a log expression with a base of 10 or a base of e. Now again, this is helpful if you're trying to simplify a log expression, and let's say that it's log base 3, but you don't have a log base 3 button on your calculator. What you can do is you convert that into log base 10, which you can then calculate with a calculator, or log base e. Either one of those, your scientific or graphing calculator should have a button for. And now that we've covered each one of these formulas basically, let's look at everything more in depth. Okay, so at this point we're going to move to our examples, starting with problem number 11. Here the instructions say, find each of the following. Do not use a calculator. And obviously we are going to use a calculator because that's the way we like to do things. But we're going to show you how to do this manually first and then electronically. So we're going to make use of this formula right here. Okay, log base b of b to the x equals x. And that means my goal is to turn my 125 into a 5 to some power. And so it doesn't take long to come up with the fact that 125 is 5 to the third. 5 times 5 times 5 is 125. And remember I said according to this formula, if the bases match, they cancel, and the exponent is the answer. So log base 5 of 125 can simplify all the way down to 3. And now we are going to pull up our Casio to check this. And the first thing I'd like to point out on our Casio is that we do have a log button that's got two little boxes. And this is one of the reasons I think the Casio ClassWiz is freaking sweet. You can do log any base on this calculator. So we're going to type in log base 5, move over, and put the 125. And our Casio is going to tell us, yeah, the answer is 3. So do you see that is super easy to check your manual labor with this particular calculator. All right, next example, number 15. Here we have log base 2 of a fourth. And again, we're going to try to make use of the same formula. So here our goal is to turn the 1/4 into 2 to some power. That is our goal. And so the first step is to get rid of the fraction. So I know that I can move the 4 up to the numerator. And when I do that, it's going to change the sign of his exponent. So bringing the 4 up to the top makes it 4 to the -1. And then I know that 4 is 2 squared. So we can rewrite 4 as 2 squared to the -1. And then using the properties of exponents, if you have an exponent raised to an exponent, they multiply. Gives us -2. And now we're at the point that we can use the formula. Here we have log base b of b. Notice the bases match. Log base 2 of 2. Those are going to cancel. And the exponent is the answer. And again, we're going to check that electronically. So using the log base button on the Casio, we're going to say log base 2, move over. Oh, and we have a fraction button. Makes that part super nice. So we can input it in the ClassWiz exactly the way it looked in the book. Bam! And the answer is verified. Freaking sweet. All right, next example, number 19. Again, remember it says don't use a calculator to simplify these. So we're going to do it manually and then electronically. And what I need to remind you of at this point is that log with no base showing is understood to be log base 10. So now notice that the bases match. Okay, so that's back to our other formula that says log base b of b to the x, where 10 is understood to be 10 to the 1. If the bases match, they cancel, and the exponent is the answer. Super easy if you know that log by itself is log base 10, and then with the calculator. Now, I would like to point out that the Casio has a log of any base button and an LN, and it may look like there is no regular just LOG button, but it's hidden right here. So if you want to do just regular LOG log, you're going to have to hit Shift and the negative button. It's going to give us log with an open parenthesis. So we're going to put in log of 10. And you do need to close that parenthesis, equals, and it does verify that that is a 1. Now alternately, you could also use the log any base button and put in a base of 10. And this expression is the same as what we were given. Log of 10 is the same as log base 10 of 10, and it is 1. So either way is fine on the calculator. Okay, next, number 23. This example is a little more radical, dude. Notice we have a radical expression, and we're trying to simplify this logarithm manually. So this is where you're going to have to dig deep into your bag of math tricks and remember that a radical expression can be expressed as a rational exponent. So what we're going to do is we're going to convert this to log base 3 of 3 to the 1/4 power. And now we see that the bases are the same, so they cancel, and the exponent is the answer. Again, this is super easy if you understand that radical symbols can become rational powers. And again, we're going to show how to input this on the Casio just in case you want to check your work. Here we're going to use the log any base button, log base 3 of, now we're going to have to do a 4th root. So we're going to come down and use the any root button. That is shift and X to the any power gives us the any root button. We're going to fill in a 4 for the root and a 3 for the radicand. Now notice this says exactly what the book gave us. Log base 3 of the 4th root of 3 should work out to be 1/4. Bam, and it does. Okay, next example, number 27. Here we have log base 49 of 7. And some of you may be thinking, well, I know 49 is 7 squared, but the trick is that you can't mess with the base. You can only mess with what you're taking the log of. So what we're going to have to do is we're going to have to convert this 7 into 49 to some power so that the bases will match and cancel. And this may sound pretty tricky, but if you think radical symbols, it might be a little easier because I think most people know the square root of 49 is 7. So it is possible to convert 7 into a 49 to some power if you think radical, dude. Okay, it's radical. So here's what we're going to say. We're going to have log base 49 of the square root of 49. Remember, the square root of 49 is 7. This does have to be the same as what you started with. And then we're going to convert from a radical symbol to a rational power. So square root means to the 1/2 power. That is something you should know at this point. Now that the bases match, they cancel, and the exponent is the answer. And we're going to look at the button pushes. So again, with the Casio Class Whiz, super easy with the log any base button. We're going to give that a base of 49, move over and put our 7. Bam, and it checks out. All right, next example, number 29, we have the natural log of e to the 3/4 power. In this example, you're going to have to remember what natural log represents. Remember, ln basically means log base e. So I'm going to rewrite natural log as log base e of e to the 3/4. And now you should see that the bases match. So again, if the bases match, they cancel, and the exponent is the answer. And what about the button pushes? On the Casio, we have an ln button, natural log of, and then how do we get the e? Well, that's going to be shift ln. Gives us the e to any power. Oh, and we have a fraction button, so we can make it e to the 3/4. Move over twice. Now that's important. When you're in the exponent in the denominator, you have to move over once to get out of the denominator, and then move over again to get out of the exponent. And then you can close your parenthesis, and then notice this looks exactly like what they gave us in the text. Natural log of e to the 3/4 power, and it checks out. And for our last example, number 31, this is going to be the last one of these where we have to find the following. Do not use a calculator. And I'm going to take us all the way back up to the top to remind you one of the things we covered. is that the log of any base of 1 is 0. So the log base 4 of 1, since we're taking the log of 1, that answer is going to be 0, and that's done. But what if you wanted to actually show the work? What if you wanted to know, why is it 0, Why? It's not just because I said so. Remember I said if you can get the bases to match, they'll cancel? Well, if you want to use that formula, what you're going to have to do is figure out what is 1 converted into 4 to some power. Is it possible to write 4 to some power and it be equivalent to 1? And the answer is yes. Yes, we can express that as 4 to some power. So we can say log base 4 of 4 to the 0. Remember that any non-zero number raised to the 0 power is 1. So 4 to the 0 is equivalent to 1. And now the bases match. Since the bases match, they cancel, and the exponent is the answer. So if you're wondering why is log of any base of 1 0, this is why. Because no matter what the base is, it can be written as the base to the 0 power, and it will be equivalent to 1. And then if you want to check with the calculator, you can. Okay, I can't resist. It's so fun using the calculator. Let's go log base 4 of 1. Yeah, and it's verified, okay? So from the formula, two formulas actually. Log any base of 1 is 0. And then when the bases match, they cancel as 0, and then the calculator. So there's verified 3 different ways. And that's going to do it for this series of examples. Okay, next example number 39. The instructions say convert to a logarithmic equation. Now we do have a formula for this, but I also have a little poem that I'd like to teach you that makes it super easy. The poem goes, bring the base down, switch the other 2 around. So here's how that works. First of all, the E is the base because it has a power. So we're going to bring the base down, and that becomes the base of your log. Bring the base down, switch the other 2 around. So we're going to be taking the log of t, and it's going to equal to 3. And that is converting exponential to log. Now you may need to take a step of simplification. We know that log base e can be simplified to natural log. So we're going to simplify log base e to ln of t equals 3. And we're done, converting from exponential to log. Number 43 is exactly the same concept. They want us to convert from exponential to logarithmic form. We're going to use the poem again. Let's bring the base down. That's going to become log base p. Bring the base down, switch the other 2 around. Log base p of 3 equals k. And you're done. That is all there is to that. And I would like to do one more example of those. The textbook doesn't have any examples with the exponential piece on the right-hand side, and I want to show you that the poem still works even in this format. So for this example, we're going to convert from exponential to logarithmic form, and the base is on the right. That's okay. The poem still works. We're going to bring the base down. That becomes log base 2. Notice it comes straight down, and so does the equal sign, okay? Bring the base down. Switch the other 2 around. And that gets you to your logarithmic equation. Next example, number 47, they want us to convert this time from logarithmic form into exponential form. Notice our log does not have a base showing. So a log with no base is understood to be base 10, and we need to be able to see that base to make the poem work, okay? So how does the poem go? It says, bring the base down. Now the 10 is the base of the log. So when I bring it down, the 10 is still going to be a base, which means it needs a power. Bring the base down, switch the other two around. So what does the 10 get for an exponent? It gets the -2 for a power, and the 0.01 goes to the other side of the equal sign. And that is converting log into exponential form. Bring the base down, switch the other two around. Next example, number 49. Again, they want us to convert from log to exponential form. And again, we see we have a log with no base showing, but that's okay, because we know that ln means log base e. So we're going to rewrite this equation as log base e of 30 equals 3.4012. And then we're going to convert to exponential form. We're going to bring the base down, switch the other two around. Now remember, the e is a base, so when I convert it to exponential, it's going to need a power. 3.4012 becomes e's power, and the 30 goes to the other side. And that is now written in exponential form. And just for fun, one more time, number 52, converting from log to exponential form. We're going to bring the base down, switch the other two around. So the t is a base, so the k becomes his power. Bring the base down, switch the other two around, converting from log to exponential form. Okay, the next two examples are basically calculator practice. Number 55, it says to find each of the following using a calculator, round to 4 decimal places. So on our calculator, remember, if we want to do just log log, that's going to be shift and the negative button. If you're using a different calculator, you may actually have just an log button, or you may have to find out how to get log on your calculator. But for the Casio, shift and negative is just your regular log. Remember, that is understood to be base 10 when there's no base showing. Log of 3 works out to be, yikes, not a nice number. That's okay. That's why they wanted us to use a calculator. Now we do need to round this correctly to 4 decimal places. So in the 4th decimal place is a 1. Behind that is a 2, which means the 1 stays a 1. So our answer is 0.4771. And that's all there is to that. That is done. And next, number 63. Again, they want us to use the calculator to approximate this to 4 decimal places. We want to know what is the natural log of 2. So on the calculator, we're going to hit the natural log button, input our 2, and equals. So we're going to need to round that to 4 decimal places. In the 4th place is a 1. Behind that is a 4, so the 1 stays a 1. 0.6931. And that's all there is to that. That problem is done. And again, 55 and 63 are illustrating that you do need to know how to input your expressions in the calculator and round correctly. All right, next example, number 69, it says find the logarithm using common logarithms and the change of base formula. Now, what they mean by common logarithms, it means log base 10. So notice this log is log base 4. On most scientific and graphing calculators, you don't have the ability to input the base of 4. You're only going to have the log button for log base 10 or the ln button for log base e. So how does the change of base formula work? Well, it starts with a fraction. And for common logarithms, it's going to be log of what you're taking the log of on top. And in the bottom is log of the base. Now, notice I didn't put a base on these logs, so that's understood to be 10. And that means most of you are going to have a button for that. This is the change of base formula. And the way I say this to help people remember what goes where, just remember the base in the bottom. Like in your house, if you have a basement, it's under the house. So the base is like a basement, it's in the bottom of the house. And then we can bring up our handy dandy calculator, and I'm going to do this like I didn't have this special button. I'm just going to do the regular log button. Now notice we do want to do a fraction, so I'm going to use the fraction button. Shift and negative for log. Don't forget to close your parenthesis and then move down. Shift and negative again. Log of 4. So this is using the change of base formula to calculate this expression that doesn't work out to be a nice whole integer number. And we need to round that to 4 decimal places. That would be 3.3219. And that's done. And if I stopped there, I think I would be cheating you out of some learning. So let's go back to our Casio and show you how freaking nice it is to have a log base button. This will do any base, so you can actually input this expression the way it is without having to use the change of base formula. You can simply say log base 4 of 100 and you'll get the correct answer. That is nice. Next example, number 17. This time they want us to use natural logarithms and the change of base formula to calculate this expression to 4 decimal places. So again, if I haven't made it clear, the base here at the bottom is not a friendly base. The two friendly bases are base E and base 10. So anytime your base is not a friendly base, if it's not base E or 10, you're going to need to use the change of base formula unless you have a Casio class whiz. So here's how it works. We're going to have a fraction. We're going to have in the numerator the natural log, because it says to use natural logs this time, of 15. And I said that the base goes in the bottom. So that's going to be divided by natural log of 100. So this is converting from base 100 to base E. And then you can calculate this electronically with pretty much any scientific or graphing calculator. All right, so illustrating this with the class whiz, we're going to start with our fraction button. We're going to have the natural log of 15. Move to the bottom, we're going to have the natural log of 100. And survey says 0.5880. And that is rounded correctly to 4 decimal places. And again, to illustrate just how nice it is to have a class whiz, instead of using the change of base formula, we could have simply put in log base 100 of 15, bam, and get the same correct answer. Casio class whiz, freaking sweet. Next, number 79. It says graph the function and its inverse using the same set of axes. That means in the same coordinate system. Use any method. And so the method I'm going to prefer to demonstrate this is Desmos. Although you're not allowed to use Desmos on your exams, I'm going to use Desmos to give you a better visual understanding, first of all, of how these graph, but secondly, what it means that they're inverses. So in Desmos, the first thing we're going to input is the exponential function, which was f of x equals 3 to the x. And if we look at that graph, you're going to see that that does fit the characteristics of an exponential curve. First of all, it does curve, but also remember when we talked about exponential functions, we said that every exponential function will have a horizontal asymptote. And you can see here that the x-axis is going to be the horizontal asymptote because the graph is approaching but never touching the x-axis. Now, instead of f inverse, I'm going to call the inverse function g of x. And you can actually graph a log function in Desmos. I think you could just type in log. Yeah, log, log, log. Now for the base, I'm not sure how to do that with the keyboard. So what I'm going to do is back up and show you how to get it from here with the keyboard. Go over to functions, miscellaneous, and you're going to have a log with any base. So I'm going to choose the log any base, and the base is 3. Log base 3, move over and put the x, and you're going to see that this blue graph is the log graph. Remember when we talked about inverse functions, we said that any graph and its inverse will be symmetric about the line y equals x. And do you see the reflective symmetry? That if I take the red graph and fold it across the green line, it would lay on top of the blue graph. So that does indicate that these functions are inverses. And the other cool thing is that since an exponential has a horizontal asymptote, when you flip it across, that means that your log function is going to have a vertical asymptote. And here we can see the vertical asymptote for the log is the y-axis. It's approaching but never touching. So there's a visual representation of each one of these graphs and describing how and why they are inverses of each other. So now I think it would be cool to show you how you actually start with your exponential function, and through algebraic manipulation you can convert it into the inverse function. Okay, so what did I just say? I said we're going to convert from exponential to log using the 3s method. And if you watched my lesson on inverses, you'll know what the 3s method is. So we're actually going to verify that this function is the inverse function of f of x. So what is the first s? We're going to substitute for f of x, and we're going to replace it with y. So that's going to say y is 3 to the x. That is the first s, which is substitute. The next s is switch, which means every y becomes x and every x becomes y. Okay, so that is the switch, the second s of the finding the inverse technique. And the third and final s is solve. We're going to solve for y. Now notice the y is up in the exponent spot, and at this point we have talked about the technique for converting an exponential into a log equation. So we're going to bring the base down, switch the other two around. So if I bring the base down, that's going to convert that into log base 3. Bring the base down, switch the other two around. Y equals x. And notice that that does isolate the y. That gets y by itself. And now that we're at the end of the third s, again, this is the 3s method for finding an inverse. Now that we're at the end, we can say, okay, this y now represents the inverse function, which is log base 3 of x, which is exactly what we were given. So this is how we get there. Now what about graphing? Okay, so let's start with the exponential function. And we're going to graph using a table. And we need to pick some good x's. Now, since x is all by itself in the exponent position, 3 good x's would be -1, 0, and 1. And then we need to plug those in and calculate the y values. So 3 to the -1 is the same as 1 over 3 to the 1, which is a third. So if I plug in a -1 into f of x, I'm going to get a third. If I plug in 0, we know that anything to the 0 power is 1. And then if I plug in 1, anything to the first power is itself. So real quickly, I can generate 3 ordered pairs for the exponential function. Now, what I'm about to say is super important. Are you listening? Since I know that this function is the inverse of our exponential, that means that these 3 ordered pairs are going to work for the inverse. All I need to do is switch their order. That is what makes an inverse function super easy to graph if you already know points from your original function. So our first ordered pair would be a third -1, and then 1, 0, and then 3, 1. That is one of those basic concepts that you need to understand about inverse functions, is that it means you just switch the x's and y's. And now we can graph both of these functions on the same coordinate system manually. All right, so here we go. For the exponential function, if I go to -1, I'm up at a third, which is not very high. 0 is at 1, and 1 is up at 3. And so we can see that this graph, I'm going to do it in blue, takes on the curve of an exponential, where the x-axis is the asymptote. It's the line that the graph approaches but never touches. And then in red, we're going to graph the inverse function. So if I go to a third on the x-axis, I'm going to be down at 1. I'm going to be at 1, 0. And if I go over to 3, I'm going to be up at 1. And again, I can see that this graph is going to curve like so, where the y-axis is the vertical asymptote. And so there is the graph of each function in the same coordinate system. And notice that they are symmetric about the line y equals x, which if they're inverse functions, they have to have that symmetry. A couple more things about log functions, okay? Every log function is going to curve. Every log function will have a vertical asymptote. It does also ask us to give the asymptotes and the domain for each function. So for the exponential function, the horizontal asymptote is going to be y equals 0. The exponential graph is going to have a horizontal asymptote. And remember, horizontal lines are always in the form of y equals some constant. And since it's at the x-axis, it's going to be y equals 0. Now, for the log function, every log function has a vertical asymptote. Vertical lines are in the form of x equals a constant. And since our vertical asymptote is the y-axis, the vertical asymptote equation is going to be x equal to 0. The domain in interval notation of the exponential graph is going to be -infinity to infinity. And that's because this graph will go forever to the left And as it comes up, it's also going to continue to scoot over and go to the right forever. So the exponential graph is going to cover all x values from minus infinity to infinity. That means the domain is all real numbers. Notice for the log function, though, if we're looking at the domain, there is no graph to the left of the y-axis. So that means that our domain for the log function is going to be restricted. Now, since the vertical asymptote is the line that the graph approaches but never touches, that means that we're going to start at 0, but we're not going to be able to include 0. So that's going to be parenthesis 0 to infinity, because this graph will start at 0, but since it's where the asymptote is, it can't include 0. So 0 to infinity, where 0 is not included. And that is going to be the domain of our logarithmic function. All right, last example, number 83. Here the instructions say graph the function, give the domain and the vertical asymptote of each function. So I guess the easiest place to start is how to identify the vertical asymptote for a log function. Pretty easy. All you need to do is take the stuff that you're taking the log of. Here it's the x plus 3. You want to set that equal to 0 and solve, and that will give your vertical asymptote. So moving the plus 3 over is going to give us x equal negative 3. And there's the vertical asymptote found. Now, if we want to, we can go ahead and go to the coordinate system and graph that vertical line. Going to x is negative 3. And normally, asymptote is represented as a dotted line. So there's our vertical asymptote. Now, what I normally teach my students, I say the easiest way to graph a log function is to not graph a log function. What you want to do is convert your function into exponential form and graph an exponential function. Let me show you how that works. Okay, so the first thing you want to do is replace f of x with y. Here we're going to have y equals log base 2 of x plus 3. And then you want to use the poem to convert log to exponential. So we're going to bring the base down, switch the other two around. Now the 2 is the base of the log. When it comes down, it's going to have an exponent because it's a base. Bring the base down, switch the other two around. So the y is going to become the exponent of the 2, and the x plus 3 goes to the other side of the equal sign. Then we want to go ahead and move the plus 3 over so that we get x by itself. So we're going to have x equals 2 to the y minus 3. Okay, now in my opinion, this equation is going to be much easier to find ordered pairs for than trying to find numbers that work in your log function. Okay, let's look at that. So for our table of values, since the y is the independent variable, what that means, it means that x is the isolated variable. What we want to do is we want to pick numbers for y and plug them in to find x. And the easiest numbers to go with here would be negative 1, 0, and 1. And then we're going to plug those in and work them out. So 2 to the negative 1 minus 3. 2 to the negative 1 is a half, and a half minus 3 is negative 2.5, and there's our first ordered pair. Next, 2 to the 0 minus 3. 2 to the 0 is 1. 1 minus 3 is negative 2. And last but not least, we have 2 to the 1 minus 3. Of course, anything to the first power is itself, so 2 minus 3 is negative 1. And now we have 3 good ordered pairs that we can plot and connect the dots. So at negative 2.5, we're going to be down at negative 1. That point is really close to the asymptote. At -2, we're at 0. That is our x-intercept. And at -1, we're at 1. Now notice that these 3 points fit the characteristics of a log function. They do curve, and they approach the vertical asymptote. So that is the easiest way to graph a log function, in my opinion. Convert to exponential, and then pick numbers for y and find the x's. Now let's talk about domain and range. The domain for a log function will be restricted. Notice the domain goes from left to right, and as I scan from left to right, I see that the graph starts at -3, but since there's an asymptote, it cannot include -3. So that means we're going to have to use a parenthesis, and this graph will go forever to the right. So the domain is going to be from -3 to infinity. And the range is bottom to top. Notice that this graph is going to go down forever, so it's going to go down to -infinity. And as it goes to the right, it is also going to continue to increase, and it will keep going up forever to positive infinity. So there's our domain and range for this particular graph. And that's going to do it for this lesson. So if you have any questions or comments about anything that I've done so far, please feel free to leave those in the comment section below, or you can text me. And thanks for watching.